I hope that you guys are having a good start to your day. Today is the 16th. Um, Looking ahead, we have our first exam on Monday, a week from today, the 23rd. That exam is going to be administered on Proctorio. So, what that means is we will not have our um, regular Zoom meeting on Monday. Instead, you'll just log into Canvas. You'll go to take the quiz, and this will be very similar to that's quiz number two, the Proctorio quiz. Um, I've extended that deadline, and I think I will again because there's still some folks who haven't taken that quiz. Um, and this is just to make sure that you have your technical issues resolved. I know that there were some suggestions that we'll make sure that you're using Chrome, and some folks ran into I'm using a Mac versus a PC. Um, I I really can't stress this enough. If you right now that quiz is open until 11 p.m. tonight. Um, it's important that you contact itac at txstate.edu to resolve whatever issue it is that you're going through, or whatever issue is that you've encountered. I know that on campus there are computers in the library, and you can use those if you need to. But getting all of the like kind of technical issues resolved before your exam next week is absolutely important. So make sure that you do that. I got a chat message. Do you know any practice quizzes you would recommend? Oh, for in preparation for the exam, I've got the study guide that I've posted on our Canvas page. And to be honest, the way that I'm going to write your exam is I'm just going to go item by item. I'm going to be like, okay, what's a question that I could come up with from that? This week, you'll have two more quizzes that will be practice exercises, basically. Just like your other ones, they'll be open note and they'll have a timer. You'll have two attempts at them. Kevin, I did see that you emailed me, and I apologize for not getting back to you. But those will be the good ways to study. And then this upcoming Friday, so we've got new content today, new content on Wednesday, but then on Friday, I'm going to reserve that for a review session. So I'll be going over, some kind of practice problems, basically. Um, so at any rate, I'm going to go ahead and proceed on. Today, what we're doing is we're talking about atomic orbitals. And there's kind of kind of blurred lines between atomic orbitals and something known as um, electron configuration. Now, everything that we're going to be talking about today is all about basically where are electrons. So this is something that we talked about last week, and we were talking about what are known as s orbitals, p or s subshell, p subshell, d subshell, and f subshell. This is like this definitely gets kind of abstract and crazy because so I want you to think about that. Think like, oh man, this whenever you have the thought of like this is kind of tricky for me to wrap my mind around, you're not the only person. So don't think like, oh, that means it's impossible. Instead, think, okay, well, that means my like brain is reading this right. Like my barometer is correct. This is tough to wrap your mind around. Now, here's basically the layout of the periodic table. Now, with the periodic table, we have a couple of different blocks: S block, P block, D block, and F block. Now, I'll go through this and then we're going to do a couple of examples. I think that's the best way to study this. So basically, this is your layout of the periodic table. I think anytime you see the periodic table or anytime you need like a sketch of it, here's what I do. Boom, boom, boom. S, P, S, D, P, and then down at the bottom, F block. There's my blocks of the periodic table. Now, what the S and p block tell us? It tells us a little bit about what are known as our valence electrons. So if we take something like nitrogen, nitrogen, a single atom of nitrogen, has 7 electrons. What's tricky about these 7 electrons is 5 of them are classified as valence electrons. Now, valence electrons are our outermost electrons, and these are the ones that determine the chemical properties of an atom. Now, another way that you can kind of decipher this, or kind of like a quick way of learning this, is when you look at the S and P blocks, anytime you look at the periodic table, you'll see a number 1, 2, and then 13, 14, 15, 16, 17, 18. What these numbers tell you is it tells you the number of valence electrons that these atoms have. So an atom of nitrogen has 5 valence electrons. It has 7 total, but only 5 valence. Now go ahead and add to the chat, how many valence electrons does an atom of bromine have? So bromine, Caitlin, great job. Okay, so bromine, when we're looking at this, what we want to do is we want to look at just the highlighted number. So although that this has a 17, this has 7 valence electrons. Everything in this row has 7 valence electrons, just like nitrogen has 15 as the number of the row or the column that it's in, but it only has 5 valence electrons. Now, I saw somebody else answered that bromine has 35. Well, bromine has 35 total, but only 7 valence. Now let's look at germanium. How many valence electrons does germanium have? And this does require a little bit of like, where's germanium, germanium, germanium? 4. You're absolutely correct. Germanium has a total of 32 electrons, but only 4 are valence. So GE, 32 total, and 4 valence. Okay. So this is very valuable because your valence electrons, they do 2 things. They determine the number, determine the chemical properties, but they also, oh, my computer is kind of funky sometimes. Um, these are what are known as your bonding electrons. Okay. So your valence electrons are your electrons that are involved in bonding between atoms. These are the ones that are going to be shared. Now, as a little poll, let's go ahead and where's my poll function? Here we go. And launch. How many valence electrons are in carbon? I'll give you another 3 seconds or so on this one. 10 more seconds. Chat. What do we have? You can um okay, so you can toggle back and forth to the previous slide. Um, yes, there will be a review for the test. Um, I guess you're calling me Lil Bro. I'm guessing I'm not younger than you, but um, yes. Yes, there will be a periodic table. For any questions that require the periodic table, I will give you access to the periodic table. And I'll show the periodic table that you're going to get for your exam on Friday. Just got little bro on Zoom, bruh, and no way. Okay. So I'm going to go ahead and stop the poll. I'm going to share the poll, share the results. Um, so yeah, it has four valence electrons. Carbon has four valence electrons. Carbon likes to share four electrons. Now, when it comes to um, classifying groups on the periodic table, what's important for you to know, recognize is the blocks. So this is our S block. This is our P block, B block, and F block. Now, one of the things that's important to know about the organization of the periodic table is that there are columns going up and down, and everything in the same column has very similar properties. For instance, right here, everything in this first row after hydrogen, these are classified as alkali metals. In the second, they are alkaline earth metals. This main block in the middle of the periodic table, these are your transition metals. And then, last but not least, well, not totally. I said last but not least, but it's not actually the last. This group over here has a couple of different groups. We've got post-transition metals. That's these guys right here. Then we've got non-metals, NM, not to be mistaken with nevermind. And then these guys right here, which are everyone's favorite like villain from a movie, the metalloids. Sounds like it's some sort of B grade alien villain from a movie or something. The last column on the periodic table, these are your noble gases. And then at the bottom, lanthanides and actinides, which actinide sounds like it's some sort of acne medicine, but I assure you it's not an acne medicine. Actinides, they're just classes. Okay, what I want you to know, these guys, these guys, these, these, and this big class of nonmetals. So let me clear all my scribbling there. I want you to know alkali metals, alkaline earth metals, transition metals, metalloids, and nonmetals. Oh, and noble gases. So there are six groups that I want you to know. And what you should expect on the exam would be questions like calcium is an example of alkaline earth metal. Select the two elements that are metalloids. Now, what I think is really helpful is let's start with those metalloids. Those metalloids are right here. And it's kind of weird. It's like a stepwise, it's like a series of stairs. Yeah, it's a series of stairs, basically. These are your metalloids. Okay. Those metalloids are distinct because, and they have a funky name because they have properties. Actually, take a second and add to the chat any metalloid which you've heard the term for. Halogens are an example of a nonmetal. Great question. Name a metalloid that you've possibly heard the term for, or you've heard that name before. And think phones, think technology, think semiconductors. Silicon, perfect, great job. Okay, so silicon is an example of a metalloid. Metalloids have properties of metals and nonmetals. Go ahead and somebody add to the chat. What do you think is a property, or what is a property of a metal to your knowledge? I'll give you this. Here's my stainless steel aluminum coffee mug cup. Yeah, it's solid and solid at room temperature. Uh, ah, ooh, conducts electricity. Perfect. Hard, possibly magnetic. Fantastic. Those are all properties of metals. Okay. Now look at the nonmetals. Think about some properties of nonmetals. This might me exhaling a compound, exhaling a mixture. Now, nonmetals, it's a great. I like it. A gas, probably a gas at room temperature, possibly burn. Great. Okay, so when it comes to metals, you've got something that's solid, something that conducts electricity. Also, something that, Yeti made billions of dollars out of this, but they don't conduct heat. Yes, non-conductive, perfect. And now that's why Yeti is unique. It's a metal that doesn't really transfer heat very well, or it's insulated so it doesn't transfer heat well. But non-metals don't transfer heat very well. Okay, so if we were to make a list of properties for metals, would be solid, conductor. Oh, great. So Yeti cups are, I believe it's just an aluminum. Um, so it's really just a matter of the my understanding is that it has a vacuum, or there is a vacuum, so it's insulated because there's a bunch of air in here, and so basically nothing can get in there, so that heat, this interior portion of the cup, um, that absorbs lots of heat, but that's separate from, or that's far enough away from part that I hold, so the heat's not directly transferred. Whereas, if you think about a coffee, like a ceramic coffee mug, you pour coffee into that and then you touch the outside. Well, that's because you're directly in contact with the surface that's getting heated. Whereas the Yeti has basically like, it's like the heated material, then a void, and then another other part of that heated material. So it's the insulation, it's the separation of them. And that's one part of it. The other part of it's marketing. They just marketed the far out of those things, and we're just like, if you like fishing, get a Yeti mug. If you like driving, get a Yeti mug. And everyone was like, I like fishing. I'm gonna get a Yeti mug. I like driving. I'm gonna get a Yeti mug because that's what I like. Okay, so properties of metals or solids, they conduct electricity, they conduct heat, whereas a non-metal, it's not a solid. And if it is a solid, it's kind of brittle, um, and it's not going to conduct heat or electricity. Well, metalloids are awesome because they have properties where they are very similar to metals, but then they have properties that make them very similar to nonmetals. For instance, silicon, microchips, which make up, my phone, my watch, my computer. There's tons of electricity running through here, but it doesn't get super hot. It doesn't get hot. It doesn't absorb. It doesn't conduct all of that electricity and all of that heat. And so as a result, I can have this phone that has tons of electricity, tons of computations running through it, and I can hold it to my face and it doesn't burn my face because there's silicon in here. Silicon, which is a metalloid, which has properties of a metal and properties of a non-metal. It's a solid, but it doesn't conduct heat. It conducts electricity, but it doesn't conduct heat. So that's what's so powerful about metalloids. They have properties similar to metals and nonmetals. Okay, so the layout of the periodic table, if you wanted to simplify it, you could say the left-hand side is your metals. The right-hand side are your nonmetals. And then separating the two are your metalloids. Everything on, everything in basically each column of the periodic table, they're going to have very similar properties. like nickel, palladium, platinum. These guys are all going to have similar properties. So that's what makes them kind of somewhat flexible, replaceable, because they're similar in their properties. Now, with that in mind, this is a link to a video that shows what happens if you got lithium, sodium, and potassium, and you put them into a solution. So I'm going to click this link. Be able to pull that one up. Do, 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 do. Okay, so we just threw lithium into this cup of water on the left. We threw sodium in the middle and potassium on the far right. Lithium, it's bubbling. That lithium is very quickly oxidizing. It's giving up an electron and then it's reacting with water. So all three of these substances are highly reactive with water. That's why, or that's one of the reasons that they're kind of in the same spot on the periodic table. Now, classifying substances as metals versus nonmetals. Okay, well, here's silicon, a silicon block. Yeah, lithium is that's a great question. So lithium's a big part of batteries. Lithium and nickel are both um, used in batteries, and lithium is one of the substances that's used in all the batteries for like electronic vehicles. That's a great question. So it's lithium ion batteries that help power electric vehicles. Um, so here's a bunch of different materials. Chlorine, well, chlorine's going to be in its gaseous state. Sulfur can form, I mean, really that kind of looks like a loofah or a, I don't know exactly. Um, sulfur, that's a chunk of sulfur. Now, if you were able to go up to that, you're to touch it, it's very brittle. It's going to fall apart very easily. Mercury over here, well, mercury, does anyone know if this is a solid, liquid, or a gas when you look at that mercury? Does anyone know what that is at room temperature? Liquid, perfect. If anyone's ever talked to like their grandparents or their parents about, whenever they were, oh, back in my day in my chemistry lab, like back in the 50s and 60s and before, they would, I don't know if I would say play with mercury, but they basically just use mercury, handle it in their bare hands, and it's a carcinogen, so that's a very bad idea. It's kind of a unique substance because room temperature, it's a liquid and it's very heavy. So it's mercury is very dense. And what people would do is they would just, they use it for their science experiment, then they pour it down the drain, then go back into the ground and the water supplies. Copper filings, those are definitely solids. Okay, so essentially what I want you to take away from this is that things that are in the same column on the periodic table have very similar properties. So everything here, if we were to look at, you know, rubidium and lithium, similar properties. Iron and ruthenium, similar properties. Fluorine and chlorine, similar. Now, there are going to be some exceptions. For example, nitrogen and bismuth. They're going to have some different but some similar properties, in part because ultimately they get classified a little differently. One thing that they are going to have in common, though, is how many valence electrons does bismuth have? Go ahead and add this to the chat. Valence electrons does Bi or bismuth have? Five. Perfect. Nitrogen has five. So, from a chemical standpoint, nitrogen and bismuth both like to participate in the same type of bonding and the same number of bonds. They both like to have five shared electrons. Okay, so valence electrons are going to give you insight into the properties of an atom. And based on that, this is the organization of the periodic table. Now, the cool thing about, or to me, one of the cool things about like chemistry and history is that this is our latest periodic table. And one of the cool things about science is that it's like, well, this is like the best that we have to date. If in the next 30 years people made some other discoveries and organized the elements a little differently, then the periodic table might shift a little bit. There might be another way that this can be organized that better represents it. Um, there in history there have been several different incarnations or several different versions of the periodic table, and so this is what we're working with right now. Okay, now what I want to come back to is this. I want to talk about these orbitals because I want you to be able to anticipate questions on the exam that relate to all this. So let's take, we're going to look at, let's look at silicon. Si. Silicon has a total of, and this is in its neutral form, it has 14 protons. So that means it has 14 electrons. Okay. Now, what this right here is valuable for, and what we can do about this is we can say a couple of things. We can say 14 protons, 14 electrons. How many valence electrons does silicon have? Well, it's got 1, 2, 3, 4, 5, 6, 7, 8. It's got 4 valence electrons. Okay. Now, with that in mind, what we want to do is we want to basically, let's imagine building a silicon atom. Now, what that means is we are going to look at the different planes in 3 dimensions where these electrons can be. Now, we're going to go bit by bit. We're going to say our very first 2 electrons within a atom of silicon will be as close to the nucleus as possible. And that is going to be referred to as the S subshell. And it's the first S. So it's 1s. Does anyone remember the exponent that we put above that? What should I put as my exponent? 2. Perfect. So I'm going to say 1s2. Okay. Now, the next place that I can put electrons is a slightly larger sphere. That's going to be the 2s2. Okay, so I'm going to shade that one in a little bit. Okay. Now, after that, I have this p subshell. This p subshell can have a total of 3 different orientations. How many electrons can each one of these 3 different, how many electrons can px, pz, and py hold? Each of them. Not the total, but each of them. 2. Px can hold 2. So py can hold 2. Pz can hold 2. So my p subshell can hold how many total electrons? 6. Perfect. Now, where it gets a little tricky is that this subshell I refer to as the 2p subshell. So I skip 1p. And I'm just drawing all these p subshells in one overlapping model. So I've got 2p6. So how many electrons have I placed total at this point in time? Got 1 vote for A. We got 1 vote for 10. 10 is the correct answer because what we do is we add up our exponents. So 2 plus 2 is 4, plus 6 is 10. So we have a total of 14 that we need to place. The first two are in the 1s orbital, the next two are in the 2s orbital, and then the next six are in the 2p orbital. Okay, so basically what I've got here, and I always like to think about this, maybe I kind of like sports. So I always like to imagine that my 1s orbital is like a ping pong ball. So I've got two electrons in that ping pong ball. Then my 2s orbital is like a baseball. Okay. A baseball is a sphere that's larger than a ping pong ball. And then my 2p, these are dumbbells. Okay. Now, what I can do and where I'm going to put my next electrons is I'm going to put them in an S subshell. What number do you think is going to go in front of that S subshell? We can look at the periodic table and say, okay, well, this is our one, two, three. What we're going to say is this is the 3S subshell. What should my exponent be for that S? 14, not quite. This is an S subshell, so I'm talking about one of these guys right here. How many electrons can one of these guys hold? Two. So I'm going to say 3s2. Okay. Now, the next place that I'm going to go is to the 3p subshell. Okay, before we look at our exponent, let's see how many electrons have we totally placed at this point. The 1s, we had two. The 2s, we had two more, so that brings us to four. Then the 2p, that gets us six, so now we're at 10. So 10 plus 3s2 gets us to 12. So what's our exponent above that p or following that p in 3p? Perfect, it's 2. Great job. Okay, so this is what is known as our electron configuration for silicon. 1s2, 2s2, 2p6, 3s2, 3p2. Is it because it has to equal the total number of electrons? Yes, it is. That's a great question. Okay, I'm a little confused on how you got the numbers before the lettered subshell. Great question. Okay, so one of the ways that we can kind of go through that is when we look at the periodic table. When you look at the periodic table, we've got rows on the left. 1, 2, 3, 4, 5, 6, 7. And then we've got columns. We're not so concerned or curious about the columns here. Instead, what we want to do is we want to say, okay, let's think about, we'll stick with silicon. Silicon has a total of 14 electrons. 14 electrons. Four of them are valence. Now, valence electrons tell us a couple of things. One, they tell us some properties of our substance. What they also tell us is how many outer electrons do we have? Now, what we can say then is, all right, well, silicon has four valence electrons. Where are those valence electrons? Think about these rows as basically being like energy levels. Number one would be low energy, and then high, or 7, would be high energy. And you could think about it almost as like a rank of sorts. What is the rank of the valence electrons of silicon? And to answer that question, you look over to what is the number of the row of that atom? You'd say, okay, it's three. So my valence electrons for silicon are going to be in that third rank. Does that help at all? Okay. So then if we were to look at, and I believe I mentioned this and I'm going to stand by this, the highest that we're going to go is to argon. And the reason that we're not going to go beyond argon is because things get a little bit wonky. So what I want you to be thinking of, and we'll do another example here. We'll do an example where we look at, let's go with fluorine. F. Fluorine has a total of 9 electrons, 7 are valence. Now, what is the rank of those valence electrons? Well, we can look at here and see that fluorine right here is in the second row on the periodic table. So then we can, oh, sorry, we can say, all right, does fluorine or the electrons for fluorine, do they include, is fluorine past the S block? Yes, it is. Is fluorine into the P block? Yes, it is. So that means we've got 2S and 2P. Now, does fluorine have, considering that this right here would answer information about our valence electrons. But let's go back to the beginning. Where do we start? We start with one S subshell, and we put 2 electrons in there. Now, as it turns out for fluorine, we've got a 2S and a 2P. Well, how many electrons can fit in an S subshell? 2. If we have a total of 9 electrons that we need to add, we've got 2 and 2. That brings us to 4. 2p 5 gets us our 9 total electrons. If we add the, and if then we wanted to know, well, how many valence electrons? If we didn't have the periodic table or didn't want to look back at the periodic table, we could add up the s orbital or s subshell and the p subshell electrons. Does that make sense? Can I get a thumbs up if there's a want for another example? Okay. Okay, cool. Okay, great. Kevin, I'll be right back to that question. I got a question as a private message. So if I was trying to find the electron configuration for lithium, I would only have one S and like 2S. Yeah, you'd only have the 1S subshell and the 2S subshell. Okay. Why does fluorine have a 2S and 2P automatically? That's a great question. So think of that's how I decided to start doing this one by looking at, well, what is the energy level or what is the rank? And I figured out that was 2 from the row on the periodic table. And then I said, okay, well, if I'm looking at the periodic table, I've got my, I got to clear all this out. I want to count for my S block, which includes hydrogen and helium. And then I want to account for the next level of my S block. So this is 1S, 2S. And then where is my element of interest? Well, it's fluorine. It's right here. And so then I'm going, okay, this is in the 2P, and it's going to be 2P5. Does that answer your question, Kevin? I got to scroll down. So answered. Okay. So, okay, great. I think I answered this. Okay. So one way that, the way that I got comfortable with this in kind of practice was, and the more that I practiced, I just kind of saw the pattern. So What is the electron configuration for hydrogen? It's 1s1. What is the electron configuration for helium? It's 1s2. Lithium, 1s2, 2s1. Then beryllium. So I based the so I actually here's what I yeah. So beryllium is Be has four electrons, so it's 1s2, 2s2. Then boron is 1s2, 2s2, 2p what? Carbon, 1s2, 2s2, 2p2. Nitrogen would be right here, and that is 1s2, 2s2, 2p3. Oxygen, sorry about that, everyone. It's 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. It's a 5. Neon, 1s2, 2s2, 2p6. Then sodium is going to be Na, 1s2, 2s2, 2p6, 3s1. So we have this nice little pattern. You fill up the 1s orbital, then you fill up the 2s orbital, then you fill up the 2p orbital, the 3s orbital, the 3p orbital. And basically that's the pattern that you follow. Um, and this has to do with basically where these electrons are kind of calculated and predicted to be found. Are there any 3s orbital or electron or subshell electrons? Are there any 3p subshell electrons? Now, as you go down further into the periodic table, this is your 4s, 5s, 6s, 7s. Here's your 4p, 5p, 6p, 7p. It gets a little bit tricky when you start dealing with the D block, because this is actually your 3D, even though you'd look at it and be like, oh, that's going to be on the 4. That's why we're stopping at argon. Now, I think that is this a challenge? Totally. This is tricky. This is tough to kind of wrap your mind around. But there's kind of a pattern. And the way that I personally always imagine it is if I'm building an atom, where am I putting these electrons? If I'm building nitrogen, I'm going to put my first electron in the 1s subshell. And then I'm going to put the second in the 1s subshell. So now I've got 1s2. So the very first two electrons for something like nitrogen are in the exact same place as the very first two electrons for helium or lithium or beryllium or sodium. They're always going to be in the 1s subshell and then the 2s and then the 2p and then the 3s. So to go back to this idea of uh, like a ping pong ball or a baseball, my 1s orbital, my 1s subshell, that's my ping pong ball. Then I'm going to use a baseball. It's a larger sphere. And then whenever I get to 3s, I'm going to use a basketball. It's larger. And then the 4s is going to be a beach ball. And then the 5s is going to be like when you were in elementary school, and you got to play with the massive, massive inflatable uh, beach balls, the canvas ones. That's what the 5s orbital looks like. The shape is all the same. It's a sphere. And I'm just showing the s orbit subshells here, but then you got the p subshells. Okay, so the p subshells are looking like this. It's a dumbbell shape or kind of a cloverleaf shape. Then you've got larger cloverleaf shapes to indicate other, like the 3p and so on. Okay, now Can I get a thumbs up if you think that you could identify where the valence electrons are on an exam here? In what subshell are the valence electrons for oxygen? Could you answer that question on an exam and give a thumbs up or say where those valence electrons are? Say what that valence electron configuration is in the chat. So, okay, I got a thumbs up. And then I got a question that I can answer that question that other people might have. I still don't understand the valence thing. Why is it 5 and not 15? Is the 10 column 0? What are the single number columns? Okay, it's a great question. So when you look at a periodic table, there are some periodic tables. I'm going to clear my writing here on this slide. I know that this is on this one. Oh, wait, just a second. Okay, so if I was asking for valence, then I'd drop the 1s. Okay, valence are your outermost electrons. And so when we number the columns, we say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So um, I gotta I'll go over this in just a second to address the question that I asked a second ago. Um, so when it comes to numbering your or getting the number of valence electrons, you'll sometimes see periodic tables with this numbering scheme where it's 3, 4, 5, 6, 7, 8, or 13, 14, 15, 16, 17, 18. That's one way that you'll regularly see them. Alternatively, you will sometimes see 3, 4, 5, 6, 7, 8. So when you see 13, just drop the 10. See that as 3. See this as 4, 5, 6, 7, 8. That is going to tell you the number of valence electrons. The reason is because this group right here, your transition metals, those behave in a very unique way. So the number of valence electrons that your transition metals have, it's highly variable. Like they sometimes one atom of iron can have 3 valence electrons, and then another time it can have 8, and then another time it can have 7. So that's why we kind of ignore that. So for the idea of counting your number of valence electrons, that's why we go with 1 through 8, looking at the S and P block. Okay, does that answer that question? Okay, then my question of, I'm gonna go, I'm gonna go back a couple slides. I'm gonna clear all this out. Here's the question. Where are the valence electrons of oxygen? And here are some options. So A, B, C. Let's go with 1s2, 2s2, 2p4. And then we'll go with 2s2, 2s1, and then D, 2s2, 2p4. And then secret option E, 2p6. Okay. Given this question, go ahead and add your answer to the chat for this question. The question is, where are the valence electrons? And keep in mind, all that I care about are those outermost electrons, those valence electrons. So now, if you need to, Okay. Now I'm getting lots of people who are saying A. Let's go back for a second. How many valence electrons? Add to the chat how many valence electrons does oxygen have? Oxygen has 6 valence electrons. Now, what we're looking for then is we're looking for exponents that are up to 6. What is the sum of these valence electrons? Or, sorry, what is the sum of these electrons when we add up those exponents? 2 plus 2 is 4, plus 4 is 8. So that's 8 valence electrons. So that's why A is incorrect. And I'm seeing lots of people answer B. D is correct because we have 6 valence electrons. Yes, the answer is D. Does that make sense, folks? That's a tricky question. So this is a question where I'm not intending, I don't want it to be like, oh man, that's a deceptive. Yeah, absolutely. So let's go ahead and I'm going to take this question and change it. Where are, you say, all the electrons of oxygen? I'm going to try to answer that question. Where are all of the electrons of oxygen? Oxygen has 8 total electrons. So our exponent should add up to 8. So now, yes, A. A is correct. Because remember, your valence are just the outermost ones. And this, I've changed that question, so I'm asking about all of them. So that's where you got to kind of like pay attention to the words in the questions. Okay, folks. I hope that was helpful. This has been recorded. I'm going to post it on our Canvas page a little bit later today. Um, there's going to be a pair of quizzes that are posted this week. We've got some new stuff on Wednesday, and then we're going to end the week with a review. Um, but I'm going to go ahead and stop my recording.